Hello, and welcome to today's webinar brought to you by Autodesk Water and Smart Water Magazine. I'm Cristina Novo, Technical Editor at Smart Water Magazine. We're excited to have you with us for this year's first session of the Autodesk Water Webinar Series, where we explore the latest digital innovations in water management. Last year, the Autodesk Water Webinar Series featured 6 insightful sessions covering a range of innovative topics in the water industry. These webinars, available for viewing on the Smart Water Magazine website, explored everything from digital twin technology to sustainable stormwater management and flood forecasting, all powered by advanced modeling techniques. In today's webinar, we'll look into a critical aspect of urban flood resilience: how sewer network data can impact urban flood modeling. Urban pluvial flooding, a growing concern driven by climate change and urban expansion, poses significant risks to communities worldwide. While 2D, 1D dual drainage models are among the most powerful tools for managing this type of flooding, their accuracy hinges on the quality and the completeness of the underlying sewer network data. In this session, we'll explore the effectiveness of different sewer networks using 2D, 1D hydraulic models. We're thrilled to be joined by Paolo Tamagnoni, Scientific Technical Lead and Flood Modeler at RSS Hydro. Paolo will share his research and work through case studies in Luxembourg and Spain. He will demonstrate how sewer network data completeness influences key outputs of models, like flood extent, and how flood model development can be streamlined in large urban areas. But before we dive into Paolo's case studies, we'll start with a brief introduction to Autodesk Innovative Solutions by Karin Novak, Civil and Environmental Engineer at Autodesk. Karin will set the stage for how digital tools are transforming our ability to tackle urban flooding challenges. Over the next hour, you'll gain valuable insights into the relationship between sewer network data and flood modeling accuracy. Whether you're looking to enhance your current modeling approaches or simply stay ahead of the curve in urban water management, today's session has something for you. Before we get into the main content, a few quick logistics. We encourage you to submit questions at any time during the webinar. To do so, please use the Q&A module at the bottom of your Zoom screen, and please include your name and your organization when you ask your questions. The speakers will address them during the Q&A session after their presentations. If you prefer to follow the webinar in a language other than English, you can select your preferred language for subtitles by clicking on the settings also at the bottom of your Zoom screen. And finally, by attending this session, you're eligible to earn a continuing professional development credit. To receive a certificate of attendance, please scan the QR code displayed on your screen and follow the instructions provided. And now, let's meet our speakers. Our first speaker is Karin Novak, a senior principal with Autodesk Business Consulting Practice with over 15 years of experience in the UK water sector, specializing in asset planning, operations, and regulation. Before joining the water industry, Karin worked in global data networking. Since 2022, she has been helping water utilities leverage digital tools to transform critical infrastructure management. Next, we will hear from Paolo Tamagnoni, Scientific Technical Lead and Flood Modeler at RSS Hydro. Paolo specializes in hydroclimatic hazards and flood modeling, integrating multiple techniques and software developed by institutions, universities, and private companies. His work focuses on mitigating flood risks and addressing water stress in the context of climate change. So let's get started. I'm delighted to hand the floor over to our first speaker, Karin Novak.
Thank you to everyone for joining us. I'm Karen, and I'm a civil and environmental engineer with a background in water management. I'm a principal business consultant for Autodesk in the AEC sector, which is architecture, engineering, and construction. And today, more than ever, we need to plan for water in the design phase of our infrastructure projects. So as engineers and hydraulic modelers, it's good to see you here. Okay, first I have to go through a safe harbor statement since Autodesk is a publicly listed company. So during this presentation, there may be statements regarding future events and development efforts on our products and services, and these statements are not a promise or guarantee of product delivery. Okay, so here's some background on Autodesk. We started out as AutoCAD back in the 1980s, and today we serve three main industries in the design space. There's AEC, design and manufacturing, and media and entertainment. So we believe in investing in R&D, and that's what keeps our products evolving. So we have a water product portfolio that complements our engineering and construction solutions. So all of our software fits together so that you can start with your conceptual plan and site feasibility, then do your detailed engineering design, and then pass the plans on to construction. So with an end-to-end workflow, you'll have a model at the end of your project with the asset data that you need to use as an operational tool. That's your operational model or your digital twin. So the software solution that we're going to discuss today is circled in red, and that's InfoWorks ICM, or Integrated Catchment Model. So ICM is our hydraulic model for storm and flood assessment and sewer master planning. It's our flagship product with over 35 years of development behind it. It's a fully integrated river, urban drainage, and overland flow model. And with the model, you can test scenarios and develop your high-level designs. So Paolo's going to talk about 1D and 2D modeling and what the differences are. And here's an example of an urban sewer network. And you can test storms of different intensities to see where hydraulic overload and flooding may happen. And if you notice at the bottom, there's the brown cross-section of the pipe where you can see how it fills up during a storm event and where it will overflow. So why do we need a model? Static flood risk maps that use historic data just aren't good enough anymore. Climate change is increasing the probability of extreme precipitation, and the consequence is more flash floods. And these flash floods happen when the ground stops absorbing water during short but torrential rainfall. And that can happen anywhere. It doesn't need to be near a river. So this type of flooding, it's called pluvial flooding, and it can severely affect urban areas. Because cities have a lot of pavement, the excess water also overwhelms the sewer and drainage systems. So we know that there's catastrophic impacts for people and property from flash floods. We've all seen that during 2024. But over time, there's also an impact to water quality for our rivers and streams. So here in Europe, what are we doing about it? Well, the Urban Wastewater Treatment Directive recast has a new focus on reducing pollution from stormwater overflows and urban runoff. And this is about surface water management for all cities with more than 100,000 people to start. So the proposal calls for integrated urban wastewater management plans to help reduce the impact of extreme rainfall and increasing urbanization. So most of our older cities have combined wastewater and drainage systems. So a model can be used to help create an integrated urban wastewater management plan. So with that picture in mind of why we need to do more about flood risk to help protect people, property, and the environment, I'll hand over to Paolo Tamagnone to discuss his research into how to make models work in a complex urban setting. Over to you, Paolo.
Thank you so much, Karen. Okay, let me share my screen. Perfect. Okay. First of all, good afternoon, everybody, and thanks for attending this presentation. As introduced before by Christina, today we were speaking about flood modeling, especially in urban areas, and obviously the major input data that is the sewer network. And so then we see a recent study where we analyzed how important is this kind of data into the flood modeling approach. So today, just a quick overview of the presentation. So we'll guide you through an introduction and the context of the study cases that we are gonna analyze. I will guide you through the model setup. So we analyze different scenarios to understand the quality of the data and how this quality is impacting on the flood results. The modeling scenarios, the results, and then some take-home message for the audience. So, as Karin already mentioned and gave a perfect overview of the context, we know that our cities are constantly affected by extreme rainfall and that generate pluvial flood. And this is the natural hazard that is causing more damages to our asset and people living in, especially in this moment, historical moment, high density urbanized, what I also like to call urbanscape. It is a new concept to call this kind of environment. So in order to analyze this complex system, we need, as an engineer and as engineers, we need tools that allow us to recreate, now also it's used that is, it's called buzzing word, but hydrological digital twin. So we want to create a digital representation of our cities and where we live. And the 2D, 1D dual drainage model offer a comprehensive digital framework to ingest all the data from the surface and from the underground and giving a proper and comprehensive representation of the hydrology of our cities. But obviously, this kind of model require a lot of input data. And so the big problem is that this kind of data is not always available, especially for old cities. And for example, looking at Europe, most of our, let's say, big cities have an historical city center. And so very often the drainage network, for example, dates back decades, if not centuries. And today I will go through a couple of study cases that we use 2 different cities to accomplish our studies and to achieve some results. The case studies are these two. We analyzed these 2 cities, one in Spain and one in Luxembourg. They are relatively small cities, but however with a dense urban fabric. And for the sake of the presentation, I will show you results more focusing on Differdange, the model in Luxembourg, but the study used these two case studies to repeat the same kind of analysis and to achieve the same results in order to see if it was not just case dependent, but was a kind of results that we can extrapolate and take as assumption. So let's deep dive into the model setup. That is probably the most interesting part for the flood modelers here in the audience. So a dual drainage model is a model that has to take in account of all information on the surface and underground of the underground drainage network. So here I present you the area of Differdange, where you can see, okay, the administrative border of the city span over the black perimeter, but actually the hydrological catchment that drains the water to the urban areas is the one composed by the red part. That is the one that we analyzed as 2D, 1D, so coupling the 2 information. So the red is the 2D domain. But then as is the fundamental importance. We know that we can simulate part of the catchment with 1D subcatchment, and then we can connect them in order to provide a boundary condition to the 2D domain. Then, since we are speaking about urban areas, the level of details is quite high, and in order to give a correct representation, we have to go really, we need to use a high resolution data set. And for example, for the case of Luxembourg, Luxembourg has a quite fortunate, let's say, position, because since it's a small country, for example, the state is acquiring with a high frequency, let's say, new digital terrain model of the entire country with a level of resolution of 50 centimeter. Going down to 50 centimeter DTM, it allows the modeler to see even the small micro topography characteristic that can affect the overland runoff. And for example, here I just put a screenshot of the tail of a street when we can differentiate between the micro topography concerning the road crown and also the edges of the road, meaning the curves. And this information, joined with, for example, break line, can help a lot in shaping the mesh, and then in this way properly accommodating the mesh to follow even the micro topography, and then so having a better representation of the overland runoff. Then, since we are using, in most of the cases, since we want to analyze a pluvial flood hazard, we need rainfall as an input. And so it's important to better parameterize the hydrological parameter of the model in order to have the correct rainfall runoff transformation. In this case, for example, in Luxembourg, there is the availability of an open access 20 centimeter land cover classification. This helps the modeler in having a better representation of the hydrological parameter. And then, as I also mentioned before, it's important to introduce information that can help better shaping the mesh, especially so the digital grid of the model. And for example, it is very important to have the most up-to-date cadastral information in order to know where the buildings are, especially in the new construction site, and which kind of obstruction will offer to the runoff. Or, for example, as I tend to use in my model, the break line along the curbs. So knowing where the street are and how large they are. And then it's up to the confidence of the modeler or how much information the modeler has. In order to represent correctly the drainage network, we can go even to the micro scale, so meaning the information related to the street inlet. Street inlet especially is a kind of data that is not very often available. And then I hope that the audience can confirm, but sometimes, very often is not available, but is a crucial data, and also we will show later why. And for example, for some model also, we developed some tools in order to predict where these inlets are, looking at the topography and looking at the drainage design. But, and then I will comment also later, having high resolution images, for example, the one that I was showing now with the new ML machine learning tools and visual visual segmentation and image segmentation, this is a kind of information that can also be retrieved, for example, training a model to a machine learning model to detect street inlet from aerial images. Then always let's say, tricky part of the process of flood modeling once we put all this data into the model is to understand, okay, this model actually works. This model is a representative of the reality. And so we need to pass through a calibration and validation process. And to do that, what is, as a flood modeler I usually do, I try to test my model against an historical event. And for example, people living in Central Europe, they will remember for sure the catastrophic event that occurred in July 2021, where there were big flood in Belgium, Luxembourg, and especially Germany. And we used this event, and then we tested the model against some reported information, because unfortunately it happened very often that we don't have a widespread gauging network for example, overland runoff. But usually the sensors are limited to rivers, so water levels in rivers. And sometimes, if we are lucky, there are some sensor monitoring what is the quantity of water that is flowing into the drainage network on some part of the main culverts, for example. But it's not very, very popular, this kind of approach. So what I wanted to stress here is the importance of the crowdsourcing. So retrieving information really from any kind of platform possible. Nowadays, social media are helping a lot. Satellite data are helping a lot in, for example, satellite data to retrieving which was the flood extent, but also are very useful, but very often, especially for this kind of event that are very short in time, we don't have this kind of data available. And here I just wanted to show there are some picture where we try to retrieve which was the water depth in different points of the city. And so most of the picture here have been taken by citizen from some local authority. And for example, I always laugh, but I want to show, it's nice, the picture on the top left. Actually is the owner of a Chinese restaurant, and I took the screenshot from a YouTube video. So, and then knowing, for example, the height of the brick and so on, we can retrieve which was the water depth. And all this information are important because then we can test the model against the observation. A small bracket here, the problem of doing crowdsourcing of information is that many times we know maybe we can retrieve the location of the observation, but we cannot really know the time or when this picture has been taken. Sometimes from social media, yes, because people tend to post immediately. So, but sometimes we not knowing the time of when the picture has been taken, then we don't know. We cannot easily correlate if that picture was really at the peak of the flood or was taken a bit before or a bit after. So, guiding you to the study that we conducted. So, we built many scenarios because we wanted to carry a comprehensive analysis. So, we considered 6 different yeatographs, so as input data. From a smaller return period to higher return period, so simulating and stressing the urban scape with more frequent and less frequent rainfall intensities. And then we create a different setup of the model. How? We create 14 different modeling scenarios. And to do that, we stressed a bit the concept of Strehler order. Strehler order usually is a methodology that is used for doing categorization of river network. It's not very used for drainage network, but actually is a concept that can be easily applied to a drainage network, because at the end it's just a man-made really drainage network. So it's not natural, but it's just man-made. And so with the Strehler order, basically here you see the Strehler order 1 showing you the most peripheric pipes, and usually are also the smallest. And see here, you can see the distribution of the diameter against the quantile of how many, for example, just for the sake of explaining this graph, for the trailer order one, we see that the 80% of the conduits has a diameter lower than 400 millimeters. And then as soon as a stretch of a pipe is connected to another one, then the level of trailer order increase. So meaning that the trailer order 6 are the main pipes. So the biggest pipe, the main collector of the city. So why we did this categorization? Because we created two reference two reference scenarios. The one called SC00, that is our ground truth, because it's the model with all the data inside. And then the opposite, the SC11, is without the network, so pure 2D. And then we created also other 6 different scenarios, and gradually reducing gradually removing pipes with the lower trailer order, so the smaller pipe. And also we used two different let's say variables. One was the trailer order, the one was the conduit length. So we started gradually removing the pipe with the smaller diameter and the shortest reach. And then to complicate further this, we create for these 6 different scenarios 2 different inlet configuration. The case A, where we were deleting the pipe but still keeping the inlet, so still keeping the surface drainage element, and then we were connecting these inlets directly to the closest manhole. And the other one where we were deleting this surface element, so removing all the inlets that were not connected to the remaining pipes. Sorry, it's a bit complicated, but try to follow me. So with this simplification, we created these 14 different scenarios. And here in this table, I just summarized how gradually we simplified the network from the SC00, that is the most complete one, so where the 100% of the network is inside, down to the SC06, for example, where just the 20% of the network was still kept in the model. And then the last that you see is completely zero because everything has been removed. Just the 2D component is being kept. So with this 14 model and 6 precipitation, we ran a lot of simulation. And some results that I want to show you. For example, here we overlapped the flood extent because we use flood extent as a target results, because most of the time we want to use this kind of model for pluvial flood hazard assessment, and the pluvial flood hazard assessment is expressed as flood hazard map. So we want to know how much water basically is still on the surface, and it potentially can affect our asset. And here you see some maps on some areas of the city, and in red you have the just 2D. So, and then you see here how neglecting totally the drainage network brings you a huge overestimation of the flooded areas. And instead, with the dark blue, the CS00 is the ground truth, because it's the model that contains all the information. And then you see that gradually that this flood extent increase proportionally to the level of simplification of the network. And this is for the case A, so with the one in which we kept the street inlet. What happened with the case B, when we remove the street inlet, you see that this overestimation is even bigger. So from this message, for example, I want to, but then I also will discuss later that even simplifying the network, so the pipes, so the underground system, but still keeping in the model the street inlet, so what you can see from the surface, the model has a good performance. I just go back and forth, and especially look at the picture on the left. Oh, sorry. How much it changed the flood extent by neglecting the street inlet is much more. And just I didn't mention it, but this is a simulation that we used during the calibration. So it's the real event, the June 2021. But conversely, this difference was less appreciated in some depressed area of the city where the water was naturally accumulating. But these results is mainly due to because the rainfall of June 2021 was very intense, so already was a catastrophic event, so the already was over the capacity, the entire network was over capacity. So just to say that when the drainage network is over capacity, however, the tendency of water in accumulating in the depressed area will, at the end of the day, at the end of the simulation, you see that there is not much difference between even a pure 2D model, because basically it's just one unique pond, big pond. But here, the main results of the study is when we use this index, that is a false alarm ratio. Basically, this index we use to compare the reference scenario, so the SC00, so the most complete and ground truth, against all the other simplified scenarios. And basically, the false positive is when the simplified scenarios was giving a results that was basically different from the reference scenarios. And what was interesting is to see the trend of this index, the false alarm ratio, by reducing the network data, the drainage network data. And then you see that we found that there is an exponential relationship between these. And with this graph, I want to show you especially that in the case A, where we still keep the street inlet, so the surface information, and then the surface information, as also experts they know, is something that can be easily retrieved even with a field surveys, because you can go even just with a GPS around the city and quickly just detect where the street inlet are without surveying and inspecting the underground cavities. The FAR is very low. And being very low, it means that whoever the model is performing well against the reference scenarios. Instead, in the scenarios B, in which is the configuration without the street inlets, you see that the error is exponentially growing while we are neglecting portion of the network. And especially, I would like to, usually in literature, they say that a FAR that is below 0.06, 0.05, it means that there is a good, there is a good correlation between the two models that you are comparing. And so, especially looking at the graph in the configuration B, we can see that the CS03, so the scenario 03, is almost the threshold below which, considering the 50%, almost the 50% of the network, is still bringing good results, but the neglecting more then the 50% of the network increase exponentially the error of your model. And so these are kind of results that has to bear in mind when you want to simulate an entire city, but then you don't have access to the complete data. So let's summarize the conclusion of these results. Sorry, it was a bit complex setup, but I tried to simplify, summarize the take-home message here. So, as we know, the dual drainage model requires a huge amount of data, especially high resolution data. And so the level of complexity of this kind of model compared to other, let's say, just the only 2D approaches that was the state of the art until now, let's say, or until recently, where we have this new tool that allows us to do more complex analysis. So this is the tricky part of having all this data and having to deal with this data, because also cities with this size, we are speaking about cities about 20,000 people. However, in your model, then you have thousands of pipes. For example, the deferred damage model has in total around 7,000 pipes, plus mesh with millions of elements, because you need a small triangle in order to catch the microtopography, and so are a very complex model. So the first, let's say, message is the complete network information. So when it's available, is always to use most of the information that we have, but whoever neglecting some of them can still yield to a good model. The impact of the data completeness is what we saw and what the results of these studies. The basically, especially concerning the flood extent, we can see that there is a direct relation between data completeness and the potential error that we can affect a model. So this also can be a good benchmark when once the model is set up, you go to the client and say, okay, this model is reliable, but there is a certain level of uncertainty because I don't have the full picture of the network. Then what I wanted to stress since the beginning is I call it surface versus underground, surface information versus the underground information. That, as we say, the B scenario, so removing all the surface, the surface elements, so meaning the street inlet, show a bigger error, while still keeping the surface information into the model. It brings to a good level of reliability. And instead, that this is a more, let's say, practical suggestion, the omitting, while you are building your model, omitting, so neglecting the conduits with the diameter below 400 millimeters, has a negligible impact on the maximum flood extent. So, and especially when we are speaking about flood hazard assessment, where when the rainfall intensity is very high, so you have a drastic change in time of water entering your model. Smaller pipes can generate more instabilities. So also from the practical point of view of the modeler, neglecting small elements can help you in for this creating a model that is more stable from the numerical point of view. And so I just wrap up everything in this main conclusion that implementing a model in which we take as an information of the underground network, the main collectors and the main culverts, and along with, so considering the surface inlet layout, can still yield to a reliable and precise dual drainage model that can be used for flood extent prediction and to generate the flood hazard map of those cities. So with this kind of simplification can help streamlining the modeling process, because it can make your model lighter with less element, because you will neglect all these peripheral elements that are smaller and can generate let's say, potential error and instability of your model, plus you have really a reduced number that also help the modeler in doing more, let's say, how do you say, is more handy to deal with a smaller data set rather than, for sure, dealing with a huge data set with thousands of pipe, and maybe 50% of them are very, very small. And with this last conclusion, I just give you also some references, because as a scientist, we are open to share, and we want to bring these results to the community in order to be really used. So here there is a bunch of references of scientific contribution, and especially the paper that contains and explains better what I presented you today is under review, but we are very confident that it will be published soon. And then we want to acknowledge all the people involved in this study. So first, Autodesk in supporting from the software point of view, InfoWorks ICM. Then we collaborated with the University of Coruña and the University of Florence. And with this, I thank you all, and you can reach me. I leave here on my contact. You can reach me LinkedIn or via email if you want to discuss further. Thank you so much.
Thank you to our speakers, Karin Novak, Civil and Environmental Engineer at Autodesk, and Paolo Tamagnoni, Scientific Technical Lead and Flood Modeler at RSS Hydro, for your presentations. We've seen how having detailed information on the sewer network affects the accuracy of flood models. Paolo has shown us different modeling scenarios of data quality, and we have learned that it is possible to streamline the modeling and still yield reliable flood risk assessments in large urban areas, with key information being main collectors and surface inlets, as he said in his conclusions. And with that, we're going to move to our Q&A session. So now it's your chance to be part of the discussion. Please submit your questions using the Q&A module at the bottom of your Zoom screen, and please include your name and your organization with your question. This is a fantastic opportunity to engage with our speakers directly. So we already have some questions that came in, and we'll go with the first one. From your experience, when can you use a 1D or 2D model on its own? Or do you always have to do 1D plus 2D together to get more accurate results?
Okay, thank you, Stina. I think that I can take this question. Yes, I mean, from my experience also in my flood modeling career, I moved from first pure 1D, then I moved to pure 2D, and then I'm more using the combination of the two. So this implemented this dual drainage model. From my experience, there are I mean, the beauty of having this different modeling approach is that you have more degree of flexibility in better representing the reality, or better creating a hydrological digital twin of your study area. And especially speaking about urban areas, because the main topic and where also this, especially the 1D, 2D model play the crucial role, is that many cities, and maybe many even from small cities, but big cities have been built in the history around rivers. And most of the cases, we saw that this river and be a river or even small creeks or ditches and been channelized. So basically are hidden from the people just walking on the sidewalk. And just using a pure 2D modeling approach in a rainfall runoff configuration, it brings a lot of, let's say, a huge error, especially when we neglect the culverts that are conveying the water collected into these streams. And so I just bring also the example of Differdange, where there is the river that is generated upstream of the street. Then as soon as the river that is really a small ditch is eating the urban fabric, then is immediately channelized. But then this river, it goes back to open air into a natural park, because especially for recreational purposes and for creating gathering spaces, we use water to make, let's say, the environment or parks nicer. So also now the tendency is to give back space to nature. And so we want to bring this river open air, open channel. But then sometimes the urban fabric is so dense that you need to rechannelize again. So you have this alternation of rivers or main collectors that they go underground and open air, underground and open air. So neglecting these culverts or this main collector, then it doesn't allow to the model to move a huge volume of water from one part of the catchment to another part of the catchment, especially from moving from upstream to downstream. And then I saw in different attempts around Europe, where now is in the past the flood hazard has been classified and has been mapped using fluvial model. But now the tendency is also to create this flash flood hazard map or pluvial flood hazard map. And in many cases, the modeling approach was not taking into account drainage network. And so, like, for example, especially along highways or where you have this big embankment that with, I don't know, highway on top or a railway on top. So neglecting the drainage network really, it stop the overland runoff. And so you create a huge area of accumulation of this water. And then from a flood hazard map point of view, you are creating a fake overestimation of the hazard in certain areas. And so this is one of the major, let's say, example that I can bring on the table where and when really in considering the drainage network, and so opting for a 2D, 1D modeling approach is really the key approach to adopt in order to have to yield to reliable results. Because if not, also the trade-off of this, especially 2D or 1D, is on the level of results, resolution of results that we want to achieve, and the computational effort that we can manage. Because having larger and huge area to be considered in one unique model, if you want to simulate everything as 2D with a fine mesh, it means that the computational demand is very high. And so it's not very easy to be handled by even, let's say, more classical engineer, even if, for example, InfoWorks ECM is fully parallelized and can run on GPU. And now GPU, thanks to NVIDIA, are way cheaper, and so can be afforded by most of the engineering companies. But still, the problem of the size of the model can increase exponentially the computational demand and let's say the difficulty of handling, as I say, big data set. Instead, some areas, as I showed for different angles, where I was connecting some catchment, just modeled as 1D area, because are less important, but from the flood hazard point of view, but are still important for understanding the quantity of water entering your domain of interest. In this way, having this degree of flexibility helps a lot in creating the best model that has the best trade-off between resolution, computational demanding, and complexity.
Thank you, Paola, for that very thorough explanation. We have quite a few questions in already, so if you can be slightly more brief for the next ones, we'll try to get quite a few of those.
I get passionate about it.
Very passionate, definitely. So we'll move on to a question from David Clark, Senior Professional Technical Officer at the Department for Infrastructure Rivers Directorate in the UK. How important is attenuation or flood storage in modeling to prevent urban flooding, given how difficult it is to obtain accurate data?
Okay. The storage depends how is want to be expressed, if it's more in terms of parameter or how we parameterize the model itself, because this is also another trade-off. While we can rely more on parameterization for introducing more 1D element or going to a lower resolution. So we need more an accurate representation of the parameter. But also from my experience, I saw, and when it's possible, reducing or having a high resolution model with most of the elements into the city well represented, then we can move the importance from the parameter to more the quality of the data used, and then in that case we rely more on how the model is good to solve the equation of the physical problem that we are dealing with, and let the model really run and represent the reality. So to say that is that if you are able to build a high resolution model with a high resolution data, then you can stress less on the quantification or the calibration of the parameter. For example, in terms of storage, there can be storage expressed by how much water can be retained by the microtopography or the roofs, or also in the infiltration parameter. Because, for example, I was the one promoting the implementation of the car number method even in 2D in InfoWorks ECM, because then we have more control on the initial abstraction. And initial abstraction is one of the parameters that we can use in terms of storage of the soil when we have to deal with rainfall runoff model. But in terms of importance, then summarizing is more on if you're using more a simplistic approach or a more detailed approach.
Okay, thank you very much, Paolo. We're going to move on to the next question. And this is from Rajesh Kumar NK, Hydrology and Water Resources Expert at WMDOLR in India. And the question is, how can blue, green, and gray water be segregated at the source while considering future demand and supply, as well as flood forecasting for sustainability?
Wow. What a complex question.
This is a difficult one, yes.
Yes, probably we should disaggregate a bit. But Okay, I try to answer, but from the modeling point of view, maybe. As actually Karin mentioned at the beginning, that is very important, and why, like, also one of the powerful point of this modeling approach is that we can differentiate for example, the drainage network from combined system that was the one used in the past and was one unique network conveying all the water, rainfall and black water. And instead now we are moving more on an integrated approach where we have dedicated pipes for dedicated water. So using this kind of model, you can try to, especially look in the future. Here we are speaking about flood problem in the future and sustainability. These model are helping a lot urban planners and water authorities and water manager in designing the best layout of the city, of the urban areas, and considering simultaneously the flood hazard problem, also in looking at the climate trend that we are able now to use climate model and the prediction of the climate model to simulate future scenarios. So we can apply corrective factor to our ietograph today in order to simulate potential event in the future with a higher magnitude, but that are still sort of realistic. But then in the same modeling approach, we can deal with the flood management. So designing the best blue water, let's say pipes carrying the blue water and rainwater, and combined also with the other pipes in charge of carrying the dirty water coming from buildings, factories, and then designing correctly the new wastewater treatment plant for the new urban areas in order to create a more, I will use the word sustainable, drainage network and system that can allow to preserve the integrity and the safety of people in one side, but also the safety of the nature and our rivers that will be the final collector of the water that is used in our urban areas.
Thank you, Paolo. We're going to move on to some questions more specific about modeling now. And this one is from Alexander Budrich, Head of Business Development at Nibus in Germany. And it's how do you handle inconsistencies in sensor data quality when modeling sewer networks?
Sensor, I mean, I didn't use sensor observation from sensor, as I was saying, because the cities or the case study that I analyzed, there were no, let's say, sensors spread on the network in order to have observed data. But I was more relying on the reported information from authorities and media to have an information to then compare the model against this in situ observation. What I saw from other studies in the past is that for calibrating a model, and it's very important, also crucial to understand if there are some pipes are clogged or there is a sedimentation in pipes, installing sensor into the into some pipes or manhole in order to having a near real-time monitoring of what is happening. So and then comparing the results of the observation of the sensor against the simulation results. And in this way, you can understand better what is happening in your network, or you can understand better how to force your model or calibrate your model to represent the reality. But sometimes it's not even easy, because maybe in your model, if you don't have information on the sedimentation of the pipe, so you introduce all your information in a, let's say, organized way, but you have to consider, usually, especially at the beginning, you consider that all your pipe are brand new and are clean and they are performing as the day in which they were installed. But then in the reality, somewhere in a stretch of a pipe, maybe there is a cloggage, and so the water cannot pass, or there is a lot of sediment, and then the sensor will give you another information. So that comparison can give you, in one side, a good method to calibrate and verify your model, and the other side can be a warning for the water authorities, say, okay, look, you have a problem that is an hotspot that must be solved and must be further investigated.
Thank you, Paolo. We're going to just try to squeeze in a few more questions. So there's a question from Jorge Garcia, Innovation Project Manager at INEA in Spain. How can your model be adapted to a dramatic situation like the one experienced in Valencia in Spain?
How can we, at the end, the beauty of having a digital tool like the numerical model is that you can play with whatever scenarios you want to introduce. So if you want to introduce and try to simulate a biblical rainfall, you can do that. It makes sense. I don't know. I saw here in Luxembourg as well. Sorry, I should not laugh, but because it was a tragedy. But there were people here in Luxembourg asking, say, okay, can we use the rainfall of Valencia in one of our model just to see what happened? Okay, you can play around. At the end, you do a simulation. You can see how your system behaves. But however, is always first, as a modeler, you have to reproduce in the best way possible the reality in terms of building, topography, land cover, pipes, and everything. And then you see how your urban scape behave against this hydrometeorological forcing. So for you can take any information, but you can also take an hurricane that usually is hitting Florida, and try to simulate what happen if it occurs here in the Mediterranean areas. Now we are experiencing, especially in the south of Italy, close to like Sicily. Now there is this new terminology, medicane. So it's a phenomenon that is new. But so we could in advance try to simulate this kind of extreme events into our model and then convey this information to cities to try and understand which are the main hotspot or the critical areas where the city should focus like mitigation measure or how to better design the urban areas to mitigate those kind of risks.
Thanks, Paolo. Well, in the interest of time, we're just going to take one more question. This one is from Navid Isam, Principal Engineer Water at ICOM in Saudi Arabia. And the question is, what is the best practice when receiving as-built data from various sources and new topographic data in different datums due to different agency interfaces?
Yeah. Actually, it is a very good question. Indeed, I can disclose that for implementing such kind of model, I would say probably 80% of the time is spent just for preparing the data set, the input data. The rest is modeling, calibration, simulation, and so on. But really, most of the part is how to homogenize the data that we received, as you were saying, from different authorities. Personally, in my workflow, but also in others, first you have to create your GIS environment that can be done in QGIS, ArcGIS, others, and really polishing, cleaning, and checking for errors or your data set. That is topography. If they have different datum, then you have to do georeferenciation of all this information in order to have one unique homogeneous data set. And once that is the task that takes most of the time. Once this dataset is clean, also homogenized, is polished, then you can import all these dataset into, for example, InfoWorks CCM in order to then try and building the model itself. But first, and what it takes most of the time is the creation of the input data set and really the correction, because also there are many times there are errors, especially when you when you have to deal with the drainage network. Sometimes this data set has been digitalized from old drone planimetries. And then in this kind of digitalization or transformation of the information, it very, very often you have errors. So you have elevation of manholes that doesn't match with even the topography. And so you have to spend a lot of time in preparing the good data set that you have to use as input.
Thank you, Paolo. So that's a huge portion of the time allocated to that task. This person also asked about examples and literature references for further reading. But maybe you can, I'm not sure if you want to try to answer that now or follow up with this person, because we are going to provide you with all the information.
Yeah, I say that everybody, as I left my contact, please feel free to reach me and we can have a separated discussion.
Perfect. Thank you very much. So with that final question, we're going to bring the webinar to a close. The speakers are going to be able to review the questions sent and may be able to follow up where possible. And I would like to thank them, our speakers, Karen Novak and Paolo Tamagnoni, for sharing their valuable insights with us today. Do you have any final remarks you would like to share?
I would like to share something. If there are any students on the webinar, we offer ICM for free for students and universities, and I'd like to encourage you to use it.
Yeah, I also want to encourage especially students and young professionals in adopting and let's say playing around with these kind of tools, because is the present and it will be the future of modeling techniques, and then more and more of cities and urbanscape, as I like to call them, needs to have more information to protect first us as a citizen and our asset from this natural hazard.
Thank you, Karen and Paolo. This is the future for sure. Thank you as well to our audience for joining us today. And we remind you that you can download a certificate of attendance by scanning the QR code that will be displayed on your screen. Today's session has highlighted the importance of accurate sewer network data in urban flood modeling. Using advanced 2D, 1D hydraulic models and understanding the impact of data completeness, we can improve flood predictions and enable better decisions for urban water management and flood resilience. Before we close, as a quick reminder, this webinar will be available on the magazine, on the website of Smart Water Magazine. Thank you for being with us today. And we also encourage you to check out other webinars in the Autodesk Water Webinar Series to discover more innovative solutions advancing the water industry. Thank you.